this video, I want to look at a worked example. We're going to start by letting f of x be the sine of x. And the first thing that I want to do is I want to find the average value of f over the closed interval between 0 and pi. I also want to observe that sine x is continuous on that closed interval, and hence it satisfies the hypotheses of the mean value theorem for integrals. And so the second part of our problem is to find a value for the c that's promised by the mean value theorem for integrals. The third part of the problem is simply asks us to illustrate the mean value theorem for integrals with a plot. So let's get started. To find the average value for our function over the interval between 0 and pi, we first of all want to remember that our function is the sine of x. And the average value for a function is going to be defined to be the definite integral over the interval. So I want to integrate between 0 and pi of my function, which is sine x dx, but I also have to divide by the width of the interval that I am integrating over. So I have to divide by pi minus 0. Now this cleans up to 1 over pi times the integral between 0 and pi of sine of x dx. And that is actually an easy integral to do. The antiderivative of sine x is known to be minus the cosine of x. And I simply need to evaluate that antiderivative between 0 and pi. And so I have 1 over pi times minus the cosine of pi minus a minus cosine of 0. And those two things are both easy trig values. So we have that 1 over pi outside, and inside my brackets I've got minus a minus 1 plus another 1. So my average value turns out to be 2 over pi. And let me clean up my notation there. So 2 over pi is the average value for my function sine x over the interval between 0 and pi. Now let's look at finding the c that is promised by the mean value theorem. Now we're still dealing with f of x is equal to the sine of x. And our interval is still the interval between 0 and pi. And as I said before, this function is continuous on that interval. So the mean value theorem for integrals says there is a c inside the open interval between 0 and pi such that sine of c is equal to the average value, and the average value was 2 over pi. Now, I want to kind of draw a picture because I got to think about what's going on here. So let's draw just a real quick picture. This is sort of what y is equal to the sine of x looks like between 0 and pi, and the top of that hump is at y is equal to 1. And now 2 divided by pi is certainly less than 1 because pi is bigger than 3. So there's some horizontal line here that is y is equal to 2 over pi. And I can clearly see that I am going to be getting not 1, but 2 solutions. So I'm expecting 2 solutions to the equation sine of c is equal to 2 over pi. How am I going to get my hands on them? Well, I'm also going to notice something else. That vertical line that I just drew is the vertical line x is equal to pi over 2. And one solution is less than pi over 2, and the second solution is going to be bigger than pi over 2. And that's going to let me figure out decimal values for the value of c. Now I also need to recall something that you've seen before, but it's been a while and you may need to review this stuff. There is a function called the arcsine function. And the arcsine function is the inverse function for sine. And in particular, if I look at the arcsine of the sine of c, that will be equal to c when c satisfies the inequality 0 is less than or equal to c and c is less than or equal to pi over 2. So my first solution here is just the arcsine of 2 over pi. Well, how do I get that into a decimal? So let me get a calculator up. And let me clear everything out of my calculator. And there, that's kind of what a calculator is supposed to look like. When we get a I actually want to clear one more thing. When you first open up a calculator, you probably see absolutely nothing. The main thing that I want to point out is that if it does not indicate that it's in radians up here, you need to make sure that your calculator is in radians. On my Apple's calculator, the degree thing toggles between them, and when I have a radian up here, I know that I am in radians. And so now I simply do 2 divided by pi, and that's and then hit the equal sign. That's 2 divided by pi. And now to get the arcsine, I want to do the second sine function. Once sine has that -1 on it, that is an arcsine or an inverse sine. And when I hit that, I have the arcsine of 2 over pi. So the arcsine of 2 over pi is about 0.69. So I'm going to come back over here and say this is 0.69. Now, how do I get the second value? That's the next challenge. And I've got a stray mark there, so I'm going to get rid of it. Now, this is something that it's been a long time since you've probably thought about, and it's important that you understand this stuff does come back. I want to think about the circular definitions of trig. So here's my unit circle. And 0.69 is a first quadrant angle, and that is my current C value. If I reflect that across the y-axis, I'm going to get an angle that I'm going to call theta, and the sine of theta is going to be equal to the sine of C. It's going to be equal to 0.69, and theta lives between pi over 2 and pi. In other words, theta is our second solution that we are expecting. And I want to think about, how do I find theta? Well, here's how I go about finding theta. First of all, let's draw this. Let's draw it in red. If I do theta, I get to there. But by symmetry, this angle that I'm going to be putting in this color teal, that angle is just another copy of C, because all I did was reflect that line across the y-axis. And so what I want to notice is that theta plus C is equal to pi. And since theta plus C is equal to pi, theta is equal to pi minus C. So our second solution, our second value for C, I'm going to call this one C1. Our second value that works, C2, is going to be pi minus 0.69. And I'm not going to worry too well. Let's actually get that up on the calculator as well. So we'll do pi, let's clear everything. Pi minus 0.69 is going to be, roughly 2.45. That's good enough. So C2 is 2.45. Now that means we have the two values of C that the mean value theorem promises us. So these two answers here are the answer to part B. C1 is 0.69, C2 is 2.45. Now, how do we illustrate those things? So let's look at the third part. Well, the first thing is we need to have a good graph. And I've actually taken the chance to graph this on graph paper. So it's worth graphing this nicely on graph paper. Now the next thing is I want to remember that my average value is 0.637. We figured that that's 2 divided by pi. And we also have the two values for C. All I need to do to finish the problem off is I need to draw a horizontal line for the average value and make sure that it intersects the curve at vertical lines for these two values. Now we do have to be a little bit careful. 0.637 is about 0.64, which is a little bit less than 0.65. So it's going to come in somewhere around here. And I have to draw that line over the whole interval. And now what I want to do is I want to kind of drop this line here and this line here. And now I simply need to label these lines. This horizontal line is y is equal to the average value. In other words, y is equal to 0.637. This one is our first C value. X is equal to roughly 0.69. This one here is our second C value. C is equal to roughly 2.45. And what I want to do to complete illustrate what the mean value theorem says is I want to put in some colors. I'm going to color the rectangle with a blue shading. And the rectangle goes over the entire interval. And this blue rectangle has height equal to the average value of the function, but it's also equal to f of C1 and f of C2. So my blue rectangle has height times width equal to f of C1 times pi minus 0, and that is actually equal to the average value of the function times pi. And now I'm going to color the stuff underneath the sine curve with a green crayon. So I've got this green area. And the green area is known to be the area underneath the sine curve, so it is the integral between 0 and pi of sine of x dx. And if you look at, and let me get out a nice new color, if you look at this chunk of area that is in the rectangle plus that chunk of area that is in the rectangle, they are approximately equal. In fact, if the picture is drawn correctly, they are exactly equal to that chunk of the area that is not inside the rectangle. And the mean value theorem says that the blue rectangle area is exactly equal to the green area under the curve. And that ends this example.